right, so we have that equation, sort of equation of motion for the interaction picture, approximated second order. We assume that the operators that convert the environmental fluctuations into the system Hilbert space are uncorrelated with the field fluctuations themselves or the fields themselves. We assume that the field correlation functions decay rapidly, and those are the main assumptions that we've done so far. Oh, okay, of course, second order. So that means we are assuming the interaction with the environment is relatively weak. So now what we're going to do is we're going to take a matrix element of that equation. This is very similar to what we did when we worked out how to write down, for example, the Schrodinger equation as a matrix vector, differential equation, system of differential equations. So we simply do it, and that means we write alpha alpha primed, right, on the whole thing. So we take the scalar product sort of from the left and from the right. The way we do that then is we write, so I have d by dt of rho alpha alpha primed. Right, that's what we're after. A lot of the stuff will look the same. And that goes to infinity now because we assume that the correlation of the field is decaying rapidly. We have my always forgotten sum. I put in there. We have our one and only time interval. And then I just want to make sure I keep the m's and n's straight. Probably wouldn't matter which one was which. And then we're going to write down the alphas, right? So alpha on the left with this one, A-N I-T of T minus tau, rho I of 0. So now you're seeing how we're actually going to get something out of this equation that has a bunch of operators in it. All right, so there are a lot of terms now because hidden in these commutators are the four dreaded terms. All right, so let's work them out and see how it goes. It's a little bit of work. It's something that nothing too intellectual. It's really just working them out and then noticing some clever ways to sort of substitute. Right, so that's what we'll be doing next. All right, let's take a look at how to do this, or one way to do it. So the first term, and by the first term we mean this times this times this. Right? So we've done this before, A commutating with B and C. So the commutator A with B, the commutator B and C is going to be like A, B, C, A, C, B, right, with a minus sign, right, and then so on. So we can work out all those things. And one of the terms that we'll have will look like this. And then for whatever reason in the notes, we're using alpha and alpha prime, never mind. I don't want to overcomplicate things. So we have AN. Now one of the notational simplification I want to make, I'm going to stop writing the I's all the time. Okay, we know that it's the interaction picture, otherwise the A wouldn't have any time dependence anyway. It just gets really nasty looking. T minus tau. Rho, or I'll leave the I for rho. And then this is rho I of, this is going to be 0, it's going to be a mistake. Right? Writing it all wrong with this. All right. So the way we make progress, when we have products of operators like this, there's not much you can do except to put in the identity in between. All right, so we're going to put in the identity here, and we're going to put in the identity here. The alpha and alpha primes vectors are obviously system state vectors. So we're going to put in the identity here and the identity here, and we'll just use betas for that. All right, so that means we're going to have two sum, beta, beta prime, alpha an of t, and then beta beta, then am t minus t naught, and then beta primed, and then rho I, and finally alpha primed. Okay, so something I probably could have pointed out earlier, maybe at this step before doing these terms, is a key move. This is a key move, and it's another assumption. Okay, and the basic idea is, remember this term here is the correlation function of the frequency of the bath, the field that's in the bath, right? So what does that really mean? Like if we're thinking about this in a true molecular system. So that means we have some molecule, it's surrounded by a solvent, for example, the solvent's moving around. As the solvent moves around, the electric field that the solute sees is going to be fluctuating. Somehow there's a coupling of that field to the states of the molecule. What is important in this integral here is that this decays very quickly, right? What's another way of saying that this decays very quickly? It is to say that the state of the system is changing very slowly, right? Because it's just a relative term anyway, right? So by making this decay quickly, we can assume that rho I of 0 is the same as what it will be at time t. Now, if the density was changing very rapidly, that would not be a very good approximation at all, right? But by insisting on the weak and fast decaying bath, or bath fluctuations, we can make this substitution here, which means that we can replace the 0 here with a t. I will admit I forgot the argument for that, and I saw my notes switching from the 0 to t, and I couldn't remember. Why do I do that? But this is the reason. Okay, so we have this first term, this first matrix element. Let's look at the very first term of this. Okay, what is this first term? So what we're going to do is we're backing out of the interaction picture. Right? We start the interaction picture because it's a convenient way of doing the splitting between the H0 and the HR Hamiltonian. Anyway, so let's put it back in. So alpha, by put it back in, I mean let's back out of the interaction picture. So now remember, A is going to be a constant now because we started out with a constant operator. And just keep track of what T's are in there because that's going to matter. All right, well, what's the good news? The good news is we know what U0 does to beta, right? Because beta is one of the eigenvectors of the H0 Hamiltonian. So this is going to actually become quite simple. We're going to go from the operators to a bunch of numbers. All right, so the one going to the left, we know how this works. This is going to give us with a plus sign. So we're going to have e to the 2 pi I, and then we were using epsilon. We'll switch to not having epsilon a little in a minute. An e to the 2 pi minus I times epsilon beta. All right, this is something that we've seen before, right? We've seen how to do this before. All right, so now when we move the e's around, we're going to have e, which we're doing to a 2 pi I. The plus is with the alpha, the minus with the beta, and t times an. So you see what's happening here. We have an energy gap between alpha and beta. So this is a frequency. This is something that's, it's obviously complex, but if you think of it sort of like half in some sense of a cosine, right? And so it's something that will give a phase that will spin or rotate in the complex plane with the frequency given by proportional to the energy gap between these two states, all right? And then it's multiplied overall by this operator here. And the operator, of course, is going to have to have some true operator form, like a dipole moment or something like that, that connects various states in the system. All right, so that's that. Let's make our simplification. So we're going to do epsilon alpha goes to alpha and so on. And that just simplifies the notation a tiny bit. All right. So we can do this again. So if we follow through, then what does that give us? That gives us e to the 2 pi I alpha minus beta an. All right, so that's the first term. The second term will look just like this, except it will have beta and beta primed in a different time. All right, and then the third term will also look just like this, except we'll have a beta primed and alpha prime. All right, so when we put it all together, this thing here, what? That was optimistic. I think I need more space than that. This thing here will be reduced to something pretty manageable, I would say. All right, we're still summing over beta and beta primed. All right, we have our first term, e to the 2 pi I alpha minus beta. But we're doing this for the alpha primed element. Alpha minus beta with a t. All right, we're going to put all the e's together. The second term is going to be 2 pi I beta minus beta primed. Just follow the pattern. T minus tau. Right, and then we're just going to leave the row I as is. So that will mean we have the an operator. We have to take the alpha primed element of that. Sorry, the alpha beta matrix element. That's still there. There's still the operator parts. We kind of ignored them because they're still there. So I should put them back. Alpha beta. I was so excited about the exponentials I forgot about the actual vectors. There we go. Now that's better. Maybe you noticed that and that was driving you nuts. Hopefully you're okay now. Beta primed, right? Beta primed. And then row I, which we can just leave it like that. And that is in the beta primed alpha prime. Okay, so if you do a little bit of gymnastics, and by the gymnastics I mean it takes like it took me forever to figure this out, so I don't really feel like doing it again. But what you can do is you can repack this formula into something a little bit different, and you can make it be equal to this. I'm just going to leave it as the result. Right, so you're going to add some intermediate summing to repack it. Basically breaking up some of these things, the alpha and the beta, t, and because you have so many different pluses and minuses here that you can really repack that quite a bit. So I'm just going to show you the clever way that van der Zwaan did this, which you can do. I did it once, and I'm not going to do it again. That's the first one's a tau, the second one is a t. So basically, it's a way of breaking it up so you have one exponential for tau and one exponential for t. All right, and then you have am gamma beta an alpha gamma times rho I of t and the beta primed in this new notation, matrix element of that. Okay. Remember we have a bunch of terms. We have this one times that one. That's one we just did. One of the other terms is this. Maybe I'll do it in a slightly different color so it's more clear. So they all work out the same kind of way. The process of doing this is the same. You're going to plug in the definition of the interaction picture version, put in all those time evolution operators for U naught. They operate on their own eigenbasis. You get a bunch of exponentials, and you do the interesting but tedious algebra to figure this out. So alpha, rho I is first in this one. AM t minus tau an of t alpha prime, because that's the matrix element we're after. So again, it's another one of these things. You plug in the basis, right? You're going to beta prime, and then you find that it's convenient if you redo it with an intermediate summation with this gamma in the middle. Noticing that there's a delta term, which is killing off the terms that were alpha not equal to beta. So we have gamma minus beta primed tau, and the T1 is 2 pi I beta prime minus, oops, it's not beta primed, beta prime minus alpha t. And that's multiplied by am beta primed alpha primed an alpha beta rho I t beta primed. So the challenge, the target in all of this is to try to get the rho I terms to all be the same. And that's the main reason for the repacking. All right, so that's what I called, when I think what I probably did was I wrote A, B, C, wrote all the terms out, and the last one was the one going backwards. All right, so that's what I called the last term, because it looks like the first term of all of them going to the right. Now we have the two terms where we have this one swapped. All right, and that's what I probably called the second and the third term. Okay, so what I'm going to do on the next board is I'm going to write down those. Now what you might be worried about is you might be thinking this looks ridiculous. I agree with you, this does look ridiculous. Could you imagine your whole scientific career pinned on whether you had a beta primed here or something? That would make me very nervous. Of course, it's going to get simpler. And when we do sort of an example or a simplification of this, we will find out that you can actually reduce a lot of this sort of incredible notation to a few very important and physically meaningful terms. All right, so we'll get there. All right, let's do the second and third terms, the ones with the minus signs in them. All right, so that looks like this. Alpha, it happens to be rho I and again, same tricks. Plug in the basis, do the work. This one does not require the intermediate summation to be able to get the rho to be in the right form. And just look at the difference frequencies. And then we have the taus and the t's separated, and it looks really nice. You do have a little bit more complicated difference frequency here. Yep, there's a minus sign. And then our operator part, I'll put a little X with a circle so you know it's the same, part of the same line, basically, AM. And this is beta primed, alpha primed. an alpha beta rho I T beta beta primed. All right, and the third term in quotes is this one, swapping the N and M. All right, and it's going to look very similar to this one. This is where having copy and paste would be convenient. Alpha minus beta plus beta prime. T. Boom. Then we have with its matrix element alpha beta, an matrix element beta primed alpha primed, and rho I T beta beta prime. All right, so what we've done is we've managed to convert the whole thing into this sort of set of terms. All right, so we've been working on the right-hand side of this equation. Now let's go back and work on the left-hand side of the equation so that we can figure out what to do this interaction picture business, right? So we have d by dt rho I of t. Well, we know what rho I is, right? Rho I is the u dagger not rho u naught. So we need to work that out. And then we want, of course, the matrix element of all this stuff, right? So alpha alpha primed. So we want to work this out. So we're going to do, the way we're going to do this is we're going to write down first, generically, what is d by dt of rho I when we insert the meaning of the interaction picture transformation. So that's u naught, so that's e to the plus 2I h naught t rho t, the regular rho, e to the minus 2 pi I h naught. Okay, again, we use a basis, or actually no, we're just going to do a, this one we're just doing the matrix element. So to do the alpha alpha prime matrix element of this, we plug it in. So we'll have d by dt, the e's don't care. This is going to become the, right, the e's do care, but they won't soon enough. This should not be a parentheses, right? It's just multiplied by t. Okay, we know what this does, we know what that does, and we're good. All right, so we get e to the 2 pi I alpha t and the alphas come in here to give us a alpha alpha prime. Right, we make this look nice and we end up with e to the, how did I do it, 2 pi I plus is alpha so now we have to do the math, right? So this is a derivative of two terms, so we have to know, we know how to do that. So that goes over to here. So we'll have the first times the derivative of the second. Whatever. plus the second times the derivative of the first. So we'll have the easy part. All right, and then we get back e to the 2 pi I times the derivative upstairs all right, which gives us in total e to the 2 pi I in both terms, e to 2 pi I alpha minus alpha primed t times 2 pi I alpha minus alpha primed rho alpha alpha primed plus this derivative. Okay, so we have a way of converting basically back to the Schrodinger picture. Okay, so there's going to be quite a lot of cancellation of those really complicated terms that we had in the previous bit. All right, so on the right-hand side, and this is where it's convenient. I don't want to write everything over and over again, but it's convenient to notice some features. Notice that every single term on the right-hand side, because of the way it was repacked, has rho I beta beta primed. All right, and so what you could do then is you could imagine that. So we know how to convert that. Back to the Schrodinger picture, right? You're going to put the two u's, u dagger and u naught, and that's going to give us back the exponentials again, because we're taking an expectation value. So this rho I t b beta beta primed is just equal to e to the 2 pi I, and it's the left minus the right, so beta minus beta primed t rho, normal rho of t, the beta beta prime matrix element. All right, so that's relatively straightforward. Basically what we do is we pick out this phase factor that's in front of it. Okay. Now, that's one thing. The second thing is, if we look at all the t exponentials, for example, like that one, okay, what we see is that the t exponentials have a little bit of a pattern to them. All right, so let's take a look at some of these terms. Now, I'm going to write down the t containing exponentials for the first term that we wrote down. We had e to the 2 pi I alpha minus beta t. So that came from the stuff that we already worked out. And we always left the rho I at the end, right? But then we just worked out what rho I beta beta primed is. It is always the same, right? It is the 2 pi I e to the 2 pi I, and that's beta minus beta primed. All right, so this term that you have there. But there's another term in there that was a delta function, right? The delta was put in alpha alpha primed, or beta primed, sorry. All right? So alpha primed and beta primed are the same, right? Which means that this beta primed is actually equal to alpha primed. Okay? So when we do is we work this out, what do? We're going to combine, right? So 2 pi I will have alpha. We'll have alpha, of course. We have a minus beta and a plus beta. So the betas are going to cancel. And the beta prime becomes alpha prime. So we have alpha minus alpha primed. All right, so that's the net effect of the t parts of the integrals. All right, that's interesting. So now what we're going to do is look at the rest of the term. So you'll have to look back at your notes to see this. But for the second term that we did, this is how the t's went. Well, I guess the final term was the second term. Okay, fine. So the final term, what I call the final term, which is not really the final term, it's just the way I was thinking about how you would do the commutators. So 2 pi I, this one's similar to the other one. So beta primed minus alpha primed t. The delta for this one is delta alpha beta. The second term, the one that came from the density, is the same. And so what happens in this case? In this case, we have the beta and the beta cancel. Beta prime cancel, right? And beta becomes alpha, right? Because of this. So we have e to the 2 pi I. Then we have beta becomes alpha with a positive sign, alpha minus alpha primed. Looks very similar to this, doesn't it? In fact, it looks exactly the same as that. All right, well, the second term is this one, e to the 2 pi I. This is the one where we have like all four things in there. Alpha minus beta plus beta primed minus alpha primed t. And then we have from the density operator 2 pi I beta minus beta primed. All right, and so of course the beta prime, and we get exactly the same thing again. And for the other version of the intermediate term with the minus sign, it's the same as this one. But they cancel out exactly the same way. So what that tells us is that the entire left-hand side multiplied by the e to 2 pi I alpha minus alpha primed is the same as the left side and the right-hand side, so they cancel out. All right, so that's pretty amazing. So that means that we can write down the final equation once we got rid of that sort of pesky term that was out front. So let's write it down. Let's write it in blue. This is kind of a cool equation. This is a multi-line thing. All right, so we have, oh, I don't know if that's going to be sharp enough. I think I'll use the magenta. So d rho alpha alpha primed is equal to minus 2 pi I alpha minus alpha primed rho alpha alpha primed t. And I will just pause for a minute to point out this is exactly the Liouville equation that you would have had if there was no interaction with the environment, right? And if the Hamiltonian was constant. We worked this out before. You get this difference of eigenvectors, eigenvalues. In Liouville space, remember? We had the Liouvillean. We found out the eigenvalues are the energy differences. Either way, it doesn't matter. All right, then we have minus 4 pi squared, so all the stuff we worked very hard on. We have our sums. So the n and m sum is for the different kinds of field bath operators that you have. And then we have all this sort of monkey business with the repacking these things properly. Our integral. And all this multiplied by this. This was the point we wanted to be able to take this out. All right. I think it's safe to say that this is definitely the most general form you could possibly have for the Redfield equation. In practice, you typically will not have so many, you won't not necessarily have all these different NMs, certainly if you're not working at a simple example, right? Definitely not for a simple example. The question is there a more compact way of writing this? And the answer is there is. All right. So what we can do is we can take advantage of something that we saw before, all right, which was to recognize that sometimes you can think of these, the density operator, like a matrix or like a vector, all right? And so we thought about that already. So, but here's another way. This is very similar. So remember how many elements we had when we went to Liouville space, right? We had Hilbert space operators became vectors in Liouville space, and they had 2 indices. And the operators in Liouville space had 4 indices. So it turns out, and it's not a coincidence, but it's because it's natural to think of things in Liouville space when you're dealing with the density operator, you can rewrite this entire equation in this way. Oops. So one simplification to go to this, obviously we have to have the summation of L over N, and M is going to basically vanish, which is to say we set N equals to 1 and there's only one field, type of field. That would be one way of saying that. Unless, of course, we could bring the sum in. I guess you could do that. You could bring the sum in. Never mind, I take that back. Right. Let's take that back and let's not say it. All right, so you have the sum on the betas, and then the idea is the terms in here, if you have multiple field and system operators, or multiple fields with system operators, they would be included in this term here. Okay. So this whole complicated equation can be written in this way, and all you have to do is fish out what are the different terms that correspond to these different relaxation processes. So this is the Redfield equation. You can recognize right here the ordinary evolution that you would expect to see for a system with a time-independent Hamiltonian. And then this is the thing which allows us to convert between density operator elements and other density operator elements. Right? So when you see a differential equation, you recognize usually that the coefficients are the things that sort of connect the different terms of the things on the left-hand side. If it's multiple equations, it's what connects different functions. All right, so we call this here the Redfield tensor or Redfield superoperator. Sometimes tensor. But what it is a matrix, essentially, of numbers. Now, you might wonder, what about all these integrals? How are we going to deal with that? I'm going to show you in a minute how to deal with that, what is the nature of these integrals. But presumably somebody could give you those numbers, and if you knew those numbers, you could work this out. Why are they numbers? They're numbers because the integral is over time. See this? These are all integrals over time. Notice what you have in here. You have something that looks like 2i omega tau, and you have a function of tau. Same here. It looks like a omega, which is different omega, function of that. Right? And this, and the function of that. In other words, we're going to be able to represent all of the terms that involve the fluctuations of the fields as a frequency domain function, which will be called J of omega. And it's simply related to the Fourier transform of the fluctuations of these fields. The J's, which I will show you in a minute how to think about them, these are called spectral densities, or spectral density functions. All right, and it's very common to think of them this way. And then what people will do is they'll say, okay, let's assume we have the system Hamiltonian, we have a coupling to the bath, which we're going to model with some, whatever it is, some operator that we need to be able to take matrix elements of. Could be linear coupling. You know, if we think of the system as a harmonic oscillator, then we know how to write the position momentum operators for the harmonic oscillator using the creation and annihilation operators, for example. Then we can write down Q, right? We could write the position as A plus A dagger divided by square root of 2. If this depends on Q, then we can write down, okay, what happens is the field fluctuates and it moves the particle around, changes the position a little bit. That's a way to think about that. All right, that's going to add a coupling that's linear. Maybe you have some fluctuation of the field, or that you think the bath fluctuates in a certain way. So that's going to allow you to include the effects of that fluctuation. When you do the Fourier transform, it'll have a particular number. And what's going to matter is it's going to matter what the function is at the frequency gap that your molecule has. Right? That's what's going to matter. What's going to matter is the spectral density at the energy difference that you're considering for here. Okay. So that's the last bit when we sort of finish the Redfield. But to start working on the last problem set, you actually just need this. Because what we do, of course, is we go back to a two-level system, we rate the density operator for a two-level system, and I tell you what these Redfield parameters are. Then you either write down an analytical formula for that, because it's a 4x4 matrix. It turns out you can solve it. Probably not by hand, but Mathematica can do it. Or if you don't like that, you can numerically solve the Redfield equation. That's another option. And we've done, I will give you a helpful computer program that will let you do the analytical one. And then you can do, if you want to do the numerical one, you can do the numerical one by yourself. But again, if you switch it into Liouville space, it's going to be a vector, a matrix, a vector. You can just plug it into any linear algebra differential equation solver thing, like ODE, the one that we used previously, 45 in MATLAB. That'll give you it'll propagate the Redfield equation in Liouville space, matrix times vector. And if you want to come back into Hilbert space, you can do that at the end. Right? So that's what you can do. Most of the terms that we have in spectroscopy come from this: population relaxation, population energy transfer, energy relaxation, dephasing, how the coherences go away. So in the last lecture segment on this section, I will finish the spectral density and also help you interpret the different terms of the relaxation superoperator.